Biology 14.2, Section 1, Fossil Evidence of Change. The main idea for this section: fossils provide evidence of the change in organisms over time. Your essential questions, although this is a very small chapter, are quite large. What are the similarities and differences between Earth's early environment and Earth's current environment? What is the typical sequence of events in fossilization? How are the different techniques for dating fossils used? And what are the major events on the geologic time scale? Earth formed about 4.6 billion years ago, and gravity pulled the densest elements to the center of the planet. About 500 million years ago, a solid crust formed on the surface. The gases that likely made up the atmosphere are those that were expelled by volcanoes, such as water vapor, carbon dioxide, sulfur dioxide, carbon monoxide, nitrogen, and hydrogen. Minerals in the oldest known rocks suggest that the early atmosphere had little to no free oxygen. A fossil is any preserved evidence of an organism. 99% of the species that have either ever lived are now extinct, but only a small percentage remain as fossils. Most organisms decompose before they have a chance to become fossilized. You'll want to know the different types of fossils. So nearly all fossils are formed in sedimentary rock. The sediment builds up until they cover the organism's remains. Then minerals replace the organic matter or fill the empty pore spaces of the organism, or the organism decomposes and leaves behind an impression of its body. So again, knowing the different types of fossils will be important for you this section. Scientists who study fossils are called paleontologists. Relative dating is a method used to determine the age of rocks by comparing them with those in other layers. Relative dating is based on the law of superposition, which states that younger layers of rock are deposited on top of the older layers. Radiometric dating uses the decay of radioactive isotopes to measure the age of a rock. Technique depends on knowing the half-life, the time it takes for half of the original isotope to decay of the isotope in question, and you learned about this freshman year.
The tale of life on Earth has been unfolding for about 4 billion years, and we humans are just the last word on the last page of that story. At least so far. And the vast stretches of time that are covered by the history of life can be hard for us to fathom. We rack our brains trying to imagine what a few hundred years looks like, let alone billions of years. And like speaking for myself, I can't even remember what I had for breakfast this morning. So to help us really appreciate the full expanse of time, scientists have turned to the rocks. By looking at the layers beneath our feet, geologists have been able to identify and describe crucial episodes in life's history, from bursts of evolutionary diversity to disastrous extinction events. These key events of new life and sudden death frame the chapters in the story of life on Earth. And the system that we use to bind all these chapters together is the geologic timescale. First, let's talk about the history of geologic time itself, because figuring out how to read history in rocks was not easy. For much of human history, of course, we had no idea how old the Earth was, or what actually happened in deep time, or what happened in what order. But in 1669, Danish scientist Nicholas Steno published the first laws of stratigraphy, the science of interpreting the strata, or layers of rock, in Earth's outer surface. Steno argued that the layers closer to the surface must be younger than the layers below them. So the farther down you dig, he thought, the older the fossils are that you find there. Sounds legit, right? But in Steno's day, when some people thought that fossils had literally fallen from the sky for some reason, this was a pretty revolutionary idea. Building on Steno's ideas, Italian geologist Giovanni Arduino went a step further and began naming the layers of rock. In the 1760s, Arduino studied the Italian Alps, organizing their layers based on their depth and composition. The lowest layers of metamorphic and volcanic rocks he called the primary layer. Above those were hard sedimentary rocks, which he called secondary, and the top layers of softer alluvial deposits he named tertiary and quaternary. But because rock layers don't appear in the same order all over the world, there was no way for geologists to compare rocks from one location to another. Without a way to compare strata, there could be no universal timescale. Finally, in 1819, English geologist William Smith figured out the solution to this problem: fossils. By comparing the remains of ancient organisms from different rock formations, Smith could match their ages regardless of how far apart they were. For example, Smith realized that fossils of many early species of trilobites are found below ammonite fossils, which are in turn below certain kinds of shellfish. So any place in the world where you find these first trilobites, you know that you're looking at rock that's older than when ammonites lived. And even in the most ancient rocks that have little or no evidence of life, scientists can still look for signs of the very earliest major geologic events. like when continents first formed, and even when the Earth itself cooled and solidified. Thanks to the work of early geologists like Steno, Arduino, and Smith, modern scientists have used these and other clues to create what we now call the Geologic Timescale, or GTS. The GTS has been reworked many times to reflect the latest knowledge of Earth's history, and today it's organized into 5 subgroups: eons, eras, periods, epochs, and ages. Organizing time in increments like this allows us to ask questions about history on different scales. In the largest increments, like eons and eras, we can ask the biggest of big-picture questions, like, was there life on Earth at this time? If there was, what did it look like?
The geologic timescale is a model that expresses the major geological and biological events in Earth's history. This time is divided into 2 segments, the Precambrian and the Phanerozoic Eon. Epochs are the smallest units of time. Periods are composed of 2 or more epochs, which is 10 million years. Eras consist of 2 or more periods, which is around 100 million years. An eon is the longest unit of time in the geologic timescale, and this includes billions of years. Precambrian, first 4 billion years, 90% of Earth's history. Life first appears during the Precambrian. Autotrophic prokaryotes enriched the atmosphere with oxygen, eukaryotes emerged, first animals appeared, and food chains were generally short and simple. The Paleozoic Era, the ancestors of most major animal groups, diversified in what scientists call the Cambrian explosion. First life on land emerges during this era. A mass extinction ended the Paleozoic Era with 90% of marine organisms going extinct at that time. Dinosaurs, birds, and mammals evolved during the Mesozoic Era. The K through T boundary is a layer of material in between the rocks in the Cretaceous and Paleogene periods with unusually high levels of iridium. Iridium is rare on Earth but common on meteorites, suggesting a massive meteorite struck the Earth about 65 million years ago. This meteorite impact changed the climate on Earth, wiping out the dinosaurs, many marine invertebrates, and many plant species. The Mesozoic Era. Geologic change took place during the Mesozoic Era that shaped the course of evolution. Plate tectonics describes the movement of several large plates that make up the surface of the Earth. These plates, some of which contain continents, move atop a partially molten layer of rock underneath them because of convection currents, and that's a throwback again to Earth science.
Water or on land. This is the kind of top-level view we're going to take today. But the smaller increments of time, like periods and epochs, help us take a tighter focus and ask more specific questions. Like, what was the climate like during this window of a few million years? And how did life around the world adapt to it? We'll be talking about those in more detail in future episodes when we talk about each era, period by period. Okay, so let's get the biggest of big-picture views of Earth's history right now by taking a tour of all the eons and eras in the GTS. Eons are the largest slices of time, ranging from 500 million to nearly 2 billion years long, and the earliest eon is known as the Hadean. It begins with the very formation of the Earth itself, around 4.6 billion years ago, and ends 4 billion years ago. And this is the only eon that doesn't have any fossils, because back then, the world was just hell. Named after the Greek underworld Hades, the Hadean lived up to its name. The planet was racked by volcanic activity, cosmic bombardments, raging storms, and temperatures that were at times hot enough to melt rock. But even in this searing wasteland, life may have been able to form. While no fossils have been found from this eon, small amounts of organic carbon have been discovered in Hadean rocks that some experts think is evidence of the earliest life. These first organisms were tiny and single-celled, but they were eventually able to shape the future of the entire planet. So their appearance is the one major benchmark of this eon. The Hadean was brought to an end by the cooling of the crust of the Earth, setting the stage for the continents to eventually form. And this cooling marked the beginning of the next phase, the Archaean Eon, which ran from 4 billion to 2.5 billion years ago. Named for the Greek word for origin, the Archaean was once thought to be when the first signs of life appeared. But at the very least, it's fair to say it was the first time that life flourished, forming mats of microbes in the primordial seas. The fossils of these microbes left behind are called stromatolites, or sometimes stromatoliths. The very oldest of them, like those found in Western Australia, date from the Archaean. During this time, the atmosphere was mostly carbon dioxide, but the appearance of cyanobacteria was about to change all that. Then, 2.5 billion years ago, the Archaean gave way to the Proterozoic Eon, meaning earlier life. And around this time, photosynthetic bacteria, along with some multicellular forms of life, spewed tons of oxygen into the atmosphere. This probably wiped out most of the anaerobic life on Earth, but it cleared the path for crucial new organisms, including the ancestral eukaryotes, whose cells each had a nucleus and organelles wrapped up in membranes. Eukaryotes developed into the first really big, complex, and sometimes kinda weird forms of life, such as the frond-like Carnea, and the plate-shaped Dickinsonia. These new, larger organisms quickly diversified, and by 541 million years ago, we were at the doorstep of the next and current eon, the Phanerozoic. Its name means visible life, and the Phanerozoic was when life really became obvious. This is the eon that's home to trees, dinosaurs, newts, aardvarks, us humans, basically life as we know it. Whew! How are you holding up? You doing okay? We've covered about 3.5 billion years already. Just got another 500 million to go, and then we're home free. Okay, now from here, it's best to explore the Phanerozoic eon through its eras, the next level down in the divisions of time. This will let us explore more recent history in greater detail. The first era of our current eon is the Paleozoic Era, which began 541 million years ago. This chapter was defined by the diversification of visible life, and it started with a bang, actually an explosion, the Cambrian explosion. This rapid growth in diversity and complexity in the world's oceans is such a huge deal in the history of life that all the eons that came before it, the Hadean, the Archaean, the Proterozoic, they're all collectively known as the Precambrian. At the start of the Paleozoic, over about 25 million years, the fossil record suddenly reveals the appearance of complex animals with mineralized remains. You know, hard parts, shells, exoskeletons, that kind of thing. And the very first of these new animals to become truly widespread were the trilobites. They were so common all over the world that they've been used as index fossils for the Paleozoic era for centuries, ever since the days of William Smith. But the trilobites soon had competition. Fish developed teeth and jaws and came to dominate the seas, including the first sharks and armored giants known as placoderms. Meanwhile, the land, which had been barren since the formation of continents back in the Archaean, was finally being populated, first by plants and then by arthropods. By 370 million years ago, entire ecosystems had developed on primeval continents. Soon after, the earliest amphibians evolved and hauled themselves out of the water, leaving their first vertebrate footprints in the mud. 299 million years ago, the supercontinent of Pangaea had formed, with an enormous desert at its center. This desert was quickly populated by the ancestors of what would eventually become reptiles and mammals, the Cenozoic. This is our era, in more ways than one. It's the era that we're in today, and it also marks the rise of the mammals. Soon after the KPG extinction, the climate warmed, and jungles stretched across the planet. Mammals quickly recovered in this hothouse world, and by 40 million years ago, most of the mammal groups that we recognize had come about, like whales, bats, rodents, and primates. But starting around 34 million years ago, the climate began to shift again. This time, ice caps started to grow at the poles, taking up much of the planet's water. And these drier conditions created a new habitat, the grassland, where ancestral horses and antelope were hunted by the first cats and dogs. It was